All right, guys. Today we're doing section 6.6, and it is on complex numbers and something called de Moivre's theorem. So we're going to get into that in a little bit, but we got to remember about complex numbers. So we're in section 6.6, and the first thing that we're going to talk about is something called the complex plane. Remember that complex numbers are in the form of a plus bi. You can't graph those on a normal plane. Can't graph on what we call the rectangular plane or the Cartesian plane. That's just a fancy word for the plane that you've been using your entire life. So instead, we need to use something called the complex plane, where the horizontal axis is a real number axis and the vertical axis is made up of imaginary numbers. So we're going to use the complex plane. If I could spell, that'd be great, right? All right, so over here, I'm going to draw a complex plane. So I've got my vertical axis, my y-axis is my imaginary numbers, and then my x-axis is my real numbers. We're going to do a couple examples on this graph, but this is what a complex plane would look like. I'm going to label it just in case I forget, and then when I come back to my notes, I want to know what's going on. Complex. Let me try to write a little nicer today. Complex plane. And so we're going to do a couple examples. We are going to graph three different vectors. We're going to graph, sorry, not vectors. This is very similar to vectors. I kind of got there a little quicker than I wanted to, but I'm going to compare this to vectors in a little bit. So we're going to graph the complex number u, which is 1 plus 3i. We're going to graph the complex number v, which is 2 minus i. And then we're going to graph the complex number of u plus v, which we're going to look at what that is in a second. So we're going to start by going to u. I'm going to graph my real number first on the x-axis, and then I'm going to go up or down and do my imaginary number. So I'm going over 1, and I'm going up 1, 2, 3. So the point u is just here. This is like back to 7th grade or whatever you learned to plot points. Okay, that's point u. Now we're going to do point v, which is over 2 and then down 1. Over 2 and then down 1. So v is like right about there. In order to do u plus v, we need to figure out what u plus v is. We have to add those two together. When we add complex numbers, you add the real numbers and then you add the imaginary numbers. So 1 plus 2 is going to be 3. 3 plus negative 1 is plus 2i. So now I'm going to graph this point, 3 plus 2i. So I'm going to go over 3 on my real number axis and up 2 on my imaginary axis, and that's the point u plus v. We didn't do a ton of graphing with vectors because that's kind of when we first started doing this online learning, but if we remembered when you were adding vectors together, you went from head to tail. So like if I went from like the origin to point u, then I could graph point v from it, and I'm actually thinking I'm going to just copy and paste this guy. So that's from the origin to point v, that's their vector v, and I can bring that and go head to tail with u, and that leads up directly to where u plus v is. I could also go in the opposite direction and do v and then do plus u this way. So I could have added u on this side over here, and it gets you the same place. Okay. So I reached my point earlier than I wanted to, but this is very similar to vectors. So complex numbers and vectors are very similar, which is why we're doing it in this unit. So it's similar to vectors. And then we're also going to bring in the polar coordinate too. So, and we're bringing in that trigonometric plane and points and all of that stuff. So we are essentially bringing everything together that we've done in chapter 6. Okay, I've got a definition for you. Definition of the word modulus. Modulus. Modulus is the absolute value of a complex number. If my complex number, we'll call it Z, is A plus BI, then your modulus is going to be radical A squared plus B squared. And I hope some of you are like, wait, that looks familiar. Do you remember what word that was in our vectors? Magnitude, very good. So I'm gonna say like magnitude in vectors. How fun. Okay, so we're gonna do an example. We're gonna find the magnitude or the modulus of complex numbers U and V. We'll do that over here. We'll do example, find modulus of U. And then over here, we'll do example, find modulus of V. I hope some of you are a step ahead of me and you're already finding it. So U was 1 plus 3i. U equals 1 plus 3i. So the modulus of U is radical 1 squared plus 3 squared. Well, we know 1 squared is 1, 3 squared is 9, so that becomes radical 10, and I cannot simplify that. That's as good as it gets. Now I'm going to find the modulus for V, which we know was 2 minus I. So if V equals 2 minus I, then the absolute value of V equals radical 2 squared plus negative 1 squared. 2 squared is 4, 1 squared is 1. That equals radical 5. Awesome. Okay, now we're going to bring in the polarness trig stuff. So the trigonometric or the polar form of complex numbers, that's what we're doing next. Trig / polar form of complex numbers. We have to remember a couple things from before, and we have to look back at our graph. So if I'm going to essentially kind of copy this graph over here for the purpose of this example. Let's see, we had our little axis, and we're just going to do U, which was 3, 1, or 1 plus 3i. That's what it was. 1 plus 3i. So U was somewhere right about here. This is my I-axis. This is my real number axis. And so again, we're relating this to vectors, relating this to polar form. If I go from the origin to my point, that distance is called R. So the distance R from the origin to the point is my modulus or my magnitude. So things that we're remembering. R is my distance from origin to point, and it is my modulus or my magnitude. Those words are interchangeable right now. And remember, we can find that using this guy from above. If we define the direction angle for Z as we did with vectors, we would know that the direction angle would be here from the positive x-axis to the actual line. So that's my theta, that's my direction angle. And we would remember that the distance horizontally and then vertically could be represented as sine and cosines of r and theta. My horizontal distance would be that it would be r times cosine theta. And then my vertical distance, we called it my y, we called it my b, that's r sine theta. And then if we substitute these expressions in, then we get the trigger, the polar form of the letter z. So things to remember, I already wrote r, and I'm gonna write here as well that r is the same thing as square root of a squared plus b squared. And then I'm gonna remind us about my polar form was where your polar form was a comma b, and we knew a was the same thing as r cos theta because your x's and your cos go together, and then b is your r sine theta because y and sine go together. And then last but not least, we could find our direction angle by itself by doing inverse of tangent of your y over x or your b over a. So those are the things that we're remembering from polar coordinates. And so if I have a complex number, if my complex number is z, and that's the same thing as a plus b that we've learned a long time ago, we can rewrite that in trig form as z is r, I'm going to put parentheses because r goes with both cosine theta and imaginary number sine theta. R times cosine theta plus I sine theta. You can think about the R being involved in both of them, but usually it's simpler to write the R on the outside, so that's why I did that. All right, so that's the important thing that we're taking away from here. All right, R is the absolute value of the modulus, and theta, another thing we call theta is the argument of z. So I'm going to refer to that in a second, or you might see that in the homework, and so I want to make sure that you have an example of that. So that's the argument of z. We're going to do a couple examples with this, okay? So don't panic yet. So we'll do an example. We're going to find the trig form of the following. Find trig or polar form of, I'm going to give you two examples. First one is going to be 1 minus root 3i. And then the second one is going to be negative 3 minus 4i. Okay? So what we have to do is we have to find r and we have to find theta, and then we're going to put it into this form. So let's go for it. R, remember, is a squared plus b squared under a radical. So r equals radical 1 squared plus radical 3 squared. Well, radical 3 seemed a little scary until we realized that radical 3 squared is just 3. 1 plus 3 is going to be radical 4. Ooh, nice. We get a positive real whole number for this. 2. Okay, now I got to find theta. Theta is going to be inverse tangent of b over a, negative root 3 over 1. You may remember that from before. But if not, it's going to be a, I don't remember it from before. I think a 60-degree angle. We got to think about where this is going to be naturally, so I'm going to put it in the calculator. I guess I'm not, because my calculator doesn't work. Okay. I believe my notes from last year say that it's 5 pi over 3, and I don't remember what that is as a degree, so in the next video I'll figure that out. But let's write this in trig form for the sake of our time. So z is the same thing as 2 times cosine theta, which is 5 pi over 3, plus I sine theta, which is 5 pi over 3. All you had to do was find r and theta, and then we are done. All right, I'm going to pause this video, and the second video is going to start with this, and then we're going to do a couple more things. Okay? Catch you in a little bit.